There's a machine so complex that only one company on Earth can build it, so vital that entire nations have gone to war over. Who gets to own one, and so precise that it can etch patterns smaller than a virus onto silicon? Without this machine, your smartphone doesn't exist. Your laptop doesn't work. The modern world stops. What is this machine, and why does it hold so much power? The machine is called an EUV lithography system. It's built by a Dutch company named ASML in the small city of Veldhoven, about an hour south of Amsterdam. Only ASML knows how to make these machines, and each one costs around $150 million. Every computer chip in the world depends on lithography, the process of printing tiny circuits onto silicon wafers. But modern chips are so small, so dense, that ordinary light can't print them anymore. ASML's EUV machines use extreme ultraviolet light, a wavelength so short it gets absorbed by air itself. This story matters now because chips power everything from your phone to weapon systems. And whoever controls the machines that make chips controls the future. ASML didn't start as a giant. 1984, it was spun out of the Dutch electronics company Philips as a small venture making basic lithography tools. At the time, Japanese firms like Nikon and Canon dominated the industry. ASML was an underdog with 100 employees and a dream to compete. Through the 1990s, ASML made a bold bet. While competitors improved existing technology, ASML partnered with research labs across Europe to explore extreme ultraviolet light. The physics seemed impossible. EUV light has a wavelength of just 13.5 nanometers, far shorter than visible light. At that wavelength, even air absorbs the light. The entire system would need to operate in a vacuum. In 2010, ASML made a breakthrough, convinced Intel, Samsung, and TSMC, the world's biggest chip makers, to invest billions in its EUV program. In exchange, these companies would get early access to the machines. The partnership gave ASML the funding to push through technical roadblocks that had stumped scientists for decades. The first commercial EUV machine shipped in 2017. It was 5 years late and plagued with problems, but it worked. By 2020, ASML had no competitors left in EUV. Nikon and Canon had abandoned the race. Then geopolitics entered the picture. In 2018, the United States began pressuring the Dutch government to block ASML from selling EUV machines to China. Washington argued that advanced chips could be used in Chinese military systems. The Dutch government quietly delayed export licenses. By 2020, the ban was unofficial but real. China responded by pouring over $100 billion into building its own chip industry. But despite the investment, Chinese firms couldn't replicate ASML's EUV technology. The machine was too complex, built from components made by over 5,000 suppliers in more than a dozen countries. In 2023, the Netherlands formally banned all EUV sales to China, under pressure from the US and its allies. ASML lost its second-largest customer overnight. The global chip industry split into two camps, those who could access cutting-edge tools and those who couldn't. How does an EUV machine actually work? Core is a process that sounds like science fiction. Inside the machine, tiny droplets of molten tin are fired 50,000 times per second into a vacuum chamber. A high-powered laser blasts each droplet, vaporizing it into plasma that emits extreme ultraviolet light. That light bounces off a series of mirrors, each polished so smooth that if you scaled one up to the size of Germany, the biggest bump would be a centimeter tall. The mirrors guide the light onto a silicon wafer coated with a light-sensitive material. The pattern of a computer chip, shrunk down millions of times, is printed onto the wafer in seconds. Each EUV machine is assembled by hand in a clean room where the air is 10,000 times cleaner than a hospital operating room. It takes around a year to build one machine. ASML ships fewer than 50 per year. Why can't anyone copy it? The machine depends on breakthroughs in optics, materials science, laser physics, and software that took 30 years to develop. The mirrors are made by Zeiss in Germany using a coding process so secret the company won't discuss it publicly. The laser comes from a US firm called Comair, which ASML bought in 2013. The control software was written in-house over decades. No single country has all the pieces. Some argue the export ban on China is counterproductive. Critics say restricting access to tools will only accelerate China's determination to build its own semiconductor industry from scratch. Others point out that China has historically struggled to innovate in areas requiring extreme precision manufacturing, and the ban might delay Chinese military advancements by a decade or more. There's also debate about whether ASML's monopoly is healthy for the global economy. A single point of failure means any disruption in the Netherlands, from natural disaster to political instability, could cripple the world's chip supply. Some economists have called for Western governments to fund alternative research programs as a hedge. So far, no alternatives have emerged. China's official position is that the ban violates free trade principles and unfairly targets Chinese innovation. Beijing has publicly committed to achieving chip independence by 2030. Though independent analysts are skeptical this timeline is realistic without access to EUV technology, the story of ASML is not just about machines. It's about the engineers who spend entire careers perfecting a single mirror, coding the factory workers in Taiwan and South Korea whose jobs depend on a steady supply of new chips, and the researchers in Chinese labs working around the clock to solve a puzzle the West has already cracked. At Veldhoven, ASML employs over 23,000 people. The company transformed a quiet Dutch town into a global hub, where scientists from 140 countries collaborate on machines that didn't exist a generation ago. Families have relocated across continents to be part of this work. The stakes feel personal. For China, the chip ban has broader human consequences. Without access to cutting-edge chips, Chinese tech companies face handicaps in artificial intelligence, telecommunications, and consumer electronics. Thousands of engineers trained in advanced semiconductor design find their skills suddenly less valuable. The technological Cold War has created invisible borders that didn't exist before. Think of a computer chip like a city. The smaller and denser you can build, the more you can fit into the same space. Modern chips pack billions of transistors into an area the size of your fingernail. To print something that small, you need light with a wavelength shorter than the structures you're building. It's like trying to paint a detailed portrait with a brush the width of your arm. You need a finer tool. EUV light is that finer tool. Its wavelength is 14 times shorter than the ultraviolet light used in older machines. This allows chip makers to print features just 3 nanometers wide. For scale, a human hair is about 80,000 nanometers thick. A single virus is around 100 nanometers. The chips ASML enables are building blocks smaller than biology itself. Why does this matter beyond tech? Chips are now strategic resources like oil or steel. They power missile guidance systems, decrypt intelligence, run financial markets, and enable surveillance. Whoever builds the fastest chips has a military and economic edge. The ASML machine sits at the center of that competition. Control the machine, and you control who gets to build the future. Here's what we know for certain. ASML holds a monopoly on the machines that make the world's most advanced chips. The technology took 3 decades and contributions from dozens of countries to develop. The US has successfully blocked China from buying these machines, and no one has found a way around the restrictions yet. What we don't know is whether China will crack the EUV problem on its own, how long the Western monopoly can hold, or what happens if ASML's supply chain ever breaks. The final question is not about technology. It's about power and who gets to decide how it's shared. Scenario 1. China continues trying to build EUV machines domestically, but fails to match ASML's precision for another 10 to 15 years. Western chip makers maintain their lead. The global tech industry remains split. Scenario 2. Through sheer investment and potentially acquiring smuggled components or reverse engineering captured tools. China develops a working EUV system by 2030. The monopoly ends. Chip prices drop, but geopolitical tensions rise as the West loses its leverage. Scenario 3. A natural disaster, cyberattack or political crisis disrupts ASML's operations or supply chain. Chip production worldwide slows or halts. Prices for electronics spike. Governments scramble to secure alternative suppliers that don't exist. The most likely near-term outcome is that ASML continues shipping to Western allies and neutral countries, while the US tightens restrictions further. Japan and South Korea, both home to major chip makers, face increasing pressure to choose sides. The machine that makes the modern world is a marvel of human ingenuity and a flashpoint for global power struggles. It represents the best of what international collaboration can build, and the danger of what happens when technology becomes a weapon. If you found this story compelling, subscribe our channel and watch our next video. Taiwan's TSMC. The company holding the world hostage to understand the other half of the chip equation. These two companies, ASML and TSMC, are the twin pillars holding up the digital age,